amosite, or brown asbestos. Here you can see a sample of suspect insulating board. Firstly, the sample would be prepared and then assessed under the stereo binocular microscope. The analyst searches through a sample to locate and identify suspect asbestos fibres. Having identified the presence of fibres, the analyst assesses their morphology or shape to ascertain if they could be asbestos, and if so, which type of asbestos it is most likely to be. Amosite presents a short, straight, grey to brown coloured fibres that have a paintbrush end effect or form in small bundles. The analyst would assess the fibre by first separating them from the sample and then manipulating them under the microscope. Here you can see that amosite fibres are straight and very brittle, shattering quickly when brushed with tweezers. These fibres are mounted onto a microscope slide in an oil which shares similar optical properties to that of the suspected asbestos type. This is then assessed under the polarized light microscope by rotating the fibre and changing the settings. This first test searches for pleochroism and relief and would present as a change in colour or the fibre standing out significantly against the background. Next is the birefringence and extinction characteristics. The fibre appears to glow in the 45-degree positions, yet extincts in the 90-degree positions. This allows us to confirm we have a mineral under the microscope, or in other words, asbestos. This next test confirms whether light passes faster down the length of the fibre or across its width. We observe the orientation of the fibre when it is showing as a blue colour. This is referred to as the sign of elongation. The final check is to confirm the fibre and mounting liquid properties are a match, which is confirmed in this case by the fibre changing from gold to purple in colour as it is rotated. If all of these tests produce the correct colours or effects, it confirms that the analyst's initial prediction was correct, and these are amosite fibres. Also within insulating board, you can often identify chrysotile, or white asbestos, mixed in with the amosite. So the analyst goes back to work, manipulating the sample in search of these fibres. Chrysotile is a serpentine form of asbestos, which results in a much more flexible and curly-looking fibre than amosite. The analyst finds suspect chrysotile fibres and separates them from the sample once more. These are then assessed for the splitting nature of asbestos and their level of flexibility. Chrysotile also has a very silky surface appearance, which is referred to as its lustre. In all, 7 separate morphological properties are assessed and recorded at this stage. Suspect fibres are then taken and mounted onto a microscope slide in a liquid which shares similar optical properties to that of chrysotile. In this case, a liquid with a refractive index of 1.550. The slide is placed under the polarized light microscope and the optical properties assessed. As with amosite, chrysotile shows little colour change under plain polarized light, and also shows little to no relief. This means that the fibres seem almost invisible at this stage. Next is the birefringence and extinction. The fibres again appear and disappear, indicating a mineral, but the fibres don't glow quite as brightly as the amosite fibres did. The sign of elongation is assessed next with the pink background and should show the fibre as blue when in a northeast to southwest orientation. This indicates the light travels slower down the length of the fibre than across the width. This would be the case for all fibres except chrysidolite. Finally, the dispersion staining objective lens is inserted and the fibre colours assessed. If it is chrysotile, the fibre should change from a blue colour to a purple colour as different wavelengths of light are refracted, which we can see it does. Here we see the identification of chrysidolite, or blue asbestos, within a sample. This sample is of bakelite plastic, used historically to form products such as toilet cisterns, telephones, and door handles. First, the sample is prepared, and then, in a controlled environment, the sample is reviewed under the stereo binocular microscope in search of suspect fibres. Here you can see fibres that are blue in colour, with a straight appearance and a paintbrush-style end to it. These initial observations would suggest this is chrysidolite. The analyst separates these fibres from the sample and assesses the 7 separate morphological properties. These are colour, appearance, lustre, flexibility, tensile strength, tenacity, and elasticity. You can see fibres that break easily when manipulated, becoming short and needle-like. These need confirming as chrysidolite fibres, so a slide is prepared with a refractive index liquid of 1.700, which means it slows light so that it takes 1.7 times longer to get through the liquid than it would a vacuum, such as space. This is exactly how light reacts when it passes through chrysidolite. The analyst places the prepared slide under the stereo binocular microscope and mounts multiple suspect fibres by lowering them into the liquid. After this, a cover slip is placed over the slide, and the slide can be brought out of the dust cabinet. The slide is placed under the polarized light microscope, and the process repeated. Chrysidolite shows some pleochroism, which is a colour change, shown here as it is changing from grey to blue under plain polarised light. This hints at the fibre being chrysidolite. Next you have the birefringence and extinction testing. This must show the fibre appear and disappear as we rotate it under a setting referred to as crossed polars. This confirms we have a mineral under the microscope. Next is the sign of elongation, which in the case of chrysidolite shows the blue-coloured fibre in an orientation opposite to that we saw with amosite and chrysotile, indicating light can travel faster down the length of the fibre than it can across its width. Finally, the dispersion staining test shows a fibre that is changing between 2 shades of blue, indicating a match between the fibre and the mounting liquid, confirming the fibre is chrysidolite. At AEC, we also analyse soils for asbestos and are working with BOHS to develop training courses for the analysis of soil samples. The process is an extension of standard bulk analysis and involves assessing soil samples under the stereo binocular microscope after the material has been dried and prepared. AEC offer all 3 recognised levels of analysis. These include an assessment for the presence of asbestos-containing materials, known as Stage 1 analysis, a quantification of the amount of asbestos-containing materials within soils, known as Stage 2 analysis, and finally, a full assessment of the amount of asbestos within soils, which is known as Stage 3 analysis. This stage includes the analysis done in Stage 2, but additionally identifies fibres that may be loose in the soil and are microscopic in size. Stage 3 analysis would be of particular importance when deciding whether a large volume of soil would be classed as hazardous or non-hazardous waste. This is done through a process of careful weighing of the soil and any asbestos-containing materials identified within, and can also include the mounting of a soil solution onto a microscope slide to allow the counting and sizing of individual asbestos fibres. This in turn allows us to quantify the weight of any free asbestos fibres held within the soil sample.